So the talk here is RAID. RAID is an acronym. It stands for Rootkit Analysis, Identification, and Elimination. And I am Peter Silverman, an undergraduate college student on the East Coast. I do independent security research. I co-authored FU2 and also authored the PyMe diff, which is soon to be released. And I contribute to OpenRC, so if you have a chance, check out the site.
And my name's Jamie Butler. I wrote the Rootkit Subverting the Windows Kernel book that was released last year from Madison Wesley, and did the FU Rootkit and contributor there at rootkit.com. Currently unemployed.
Currently unemployed.
So there's the email address.
Email is there. He does not have a business card.
Actively looking for work.
He does not have a business card. Do not ask him. We put the email address in there for you guys. So if you want to get hold of him, there it is. That slide will not be on the internet. So write it down. I'll give you a second, and we're going to move on because we don't want him getting spammed more than he already does. We all good? All right. All right, so what are we going to cover here real quick? We're going to try to do as fast a review as possible. For those of you who were at the R squared, the rootkit, history of rootkits or whatever, they covered some of it. We're going to go a little more in depth. We're going to try to go quickly so we can get through to more interesting stuff. We're going to cover your userland hooks, your kernel hooks, your ERP hooks, your IDT hooks, your model-specific registers. We'll talk about process hiding. Both of us are pretty good at it. We both have written a version of FU. And just for those, those of you, it's not FU2, it's FU and version 2. So those, just to be specific. And then we'll get into RAID, and we will do a live demo. A lot of people have been showing videos. We are going to do a live demo. Props to Dino for doing a live demo, and you see what happens. So
stick around for the demo.
Yeah, if nothing else, watch the demo.
6 rootkits, 1 VMware, 1 kernel debugger, and our RAID product. We'll see what happens. So many of you already know this. Quick background. What is a rootkit? It has 2 defining characteristics. It's to provide stealth on the system. To do this, usually you have to gain execution control or modify data in the kernel. Another goal of the rootkit is to provide persistence so that you can always come back. A lot of the remote command and control stuff that Alexander will be talking about later in this track deals with that. In order to gain execution control, there's something called IAT hooks. Every executable, like Task Manager and so forth, uses imports from other DLLs, and those imports are patched up at load time, so you can hook into Task Manager or Explorer, any other Windows process, and patch the actual function that gets called on, say, a call to enumerate the files on the file system, or a call to enumerate the open ports, etc. EAT hooks, these are a little more interesting. Not a lot of people mess around with EAT hook validation or EAT validation. What the EAT can be used for is all those DLLs have a corresponding export table. They say, hey, I provide this functionality, and if you want to call it, this is where you have to call into in order to reach me. The advantage of hooking here is that device drivers, they always stay in memory. They're sitting around there at load time. Their EAT is set up properly. As new device drivers come in or other programs that want to call functions exported by the driver, they have to use the EAT. And that gives you a good place to hook in. An example of this would be Zone Alarm does EAT hooking. It actually is trying to patch a function in indis in the library it exports, which is called indis register protocol, in order to gain access to all the protocols such as TCP/IP that's available in the system. So kernel space is a great place to hook. IAT hooking isn't that interesting because that's usually a user mode technique that things like Hacker Defender and others have used in the past. However, kernel mode, the advantage of that is you have a single hook, and now you're globally jacked in to all the processes on the system. With IAT hooks, you have to get access to each individual process's address space. because they have a private address space. Therefore, if you try to hook kernel32.dll or ntdll.dll, you will only hook that process. However, once you're down at kernel mode, if you hook the system call table, etc., you hook every single process that may pass through that region of memory. Here's a diagram. Most of it showed up, I believe. So what we have here is a user mode program making a system call. That's how you request certain services of the operating system. Here we're doing a ZW create file. That will transition through the border in the center from user mode to kernel mode. In kernel mode, we're now in KI system service. KI system service handles all requests from user mode processes in order to request some functionality from the OS. It's going to look in EAX for an index into the system call table you see there. And at that index in the table is the actual address in the library NTOS kernel that's going to implement the functionality that the users requested. So in this case, it's nt create file. Here just shows you an example of what I said. The nt create file is not exported by NTOS kernel, but it resides in NTOS kernel.exe, and there is the pointer into NTOS kernel.exe. Typical rootkit subversion would be to hook into this table, modify that address to an address of its own, and then call the original function. And you might ask, why would you call the original if your whole idea was to bypass the original? Well, normally you still need the kernel to do the actions that the user requested, such as ZW query directory file would give you back all the files and so forth on a system. Well, you still need the kernel to do that for you, but when the result returns, you want the original to return to you. And then once you have the answers, you can then modify the answers before you pass them back up to user space. So an inline hook, you'll notice too at the bottom of all these slides, there's a URL for examples if we know of a good example. A lot of these come from rootkit.com where you can download and play with the example yourself. The source code is available to you. This one's called MIGBot. It does inline function patching. And with inline function patching, you're not hooking any existing table, such as the IAT or the EAT or the service descriptor table. What you're hooking instead is the actual binary in memory of the function. So in this case, you would patch some function in NTOS kernel with a jump into yourself. And then you'll see at the end, we'll call, the rootkit code would call the original function plus some offset. That offset was the amount of room we had to obliterate in the target function in order to insert our immediate jump. So another example of a hook is the ERP hooking. Every single device driver exposes a table of function pointers that will handle certain requests. Where these come into play is a normal process will say, hey, operating system, create me a socket, or create me a file, etc. However, that passes from the system call level through the system call table, and eventually hits an ERP. It's translated into an ERP, which is an IO request packet. That IO request packet is then chained to the specific device driver that handles that underlying resource, usually a hardware resource, such as the file system itself. So if you were making a call to perhaps write a file, that would eventually hit ntfs.sys, which is handling the file system for you. If you hook into that function table, you can intercept all requests for file IO or a lot of the networking IO type stuff. And there is an example in the book and also on rootkit.com. All the code from the book is on rootkit.com for free. And this is a ERP hook that I implemented that will hide all network ports by intercepting a single function to the device driver that's a query. And I can basically hide any port I want from netstat, etc. If you're doing a port scan, this isn't the method to use. Alexander may mention some ways that you can get past that type of detection. Interrupt hooking. Interrupts fire on also when the processes and other resources need the intervention of the kernel or the intervention of the underlying device driver that handles things like the network card and so forth. If you hook the IDT, you can gain execution control flow. And Shadow Walker was an example of this. It was a very advanced technique by Sherry Sparks, and also helped on that project. It was given last year, BlackHat. What that did is take over the page fault handler. If you hooked in the IDT, the 0E interrupt, you could handle all page faults. And we use that method to cloak code within the kernel. So if you're just scanning kernel memory, you have some kind of signature-based algorithm that you go look for rootkits in kernel memory. This rootkit would actually hide the presence of code so that your signature would no longer see it. Model-specific registers, they're the new IDT hooks of this decade, I suppose. This slide is specific to the Intel architecture. AMD has a similar naming convention. These are the IA32 sysenter is the one we're going to be interested here. There was actually a rootkit Rostoka that used this hook. In the MSR registers, you specify where certain things will be handled for you, such as a sysenter. A sysenter is a fast call, which you can transition quickly from user mode into kernel mode. Instead of going the old way, used to be fire off an int 2E, and now they use this faster sysenter call. If you change the registers, the MSR registers, you can register your own function to handle sysenter and so forth. And again, this was an example there of a current rootkit that's using this. And there is code on rootkit.com that'll show you how to do it. So process hiding circa 99 was the NT rootkit by Greg Hoagland. And it basically went to your system call table and patched up a bunch of functions. So that could hide registry keys, it could hide files, it could hide processes, and so forth. Then a few years later, I came around. I was working at an IDS company, and we were trying to detect some of these types of tricks. So instead of, I thought, well, looking at these tables and verifying that they're valid and so forth is a good way to go about detecting them. However, is there other types of attacks that could get around us? And I developed a proof of concept rootkit called FU that would go in and unlink the active process list so that you could take a process out of the active process list. It would still get scheduled. However, it wouldn't show up to Task Manager or any of the other processes. And we'll have the obligatory slide on this in a moment. Here it is. The slide's been running for like 4 years. I'm very proud of it. There's some steganography within the slide if you run it on your home computer. This is a demonstration of the very top box is the processor control region, the processor control block. It contains pointers to your current thread, your next thread, and your idle thread on the Windows architecture. Once you have the current thread, you can use that to jump to the current process. And once you're in the current process, these structures are supposed to be opaque to you. Microsoft doesn't want you to be editing them. However, WinDebug now allows you to see a lot of these structures on through their different architectures. However, they do change between service packs. So you have to download the symbols and load it up into WinDbg for each one and modify your rootkit. So here what we're going to do is there's flink and blink pointers in every single process, e-process block, and they point to the processes around us. And we're just going to change the flink and blink of our neighbors so that they point around us and therefore we disappear. So now, latest process hiding is 90210 discovered that, hey, him and along with Joanna, I suppose, said that there was all these processes have threads. The scheduling is really done at the thread level. So if we can find the threads, we can find the process, and therefore we can detect the hidden process. So 90210 decided that he wanted to even hide his threads, so he implemented his own scheduler within the kernel, and he removed himself from these thread lists that are in the Windows operating system. The FU2 by Peter Silverman and Chaos, what that did was there was a detection mechanism that would enumerate all the open process handles on the system. We'll get into that in a moment. And it was to subvert that. So FU2 modifies the PSP CID table. The PSP CID table's main purpose, whenever you see the third letter of a function or a variable name begin with a P, that's usually Microsoft private function or variable. They don't want you to use it, and it's not exported. So this is internal to the kernel itself, and it contains an open handle to every single process and every single thread on the system. What Fu2 did was it would find these handles and remove the handle from the table and therefore hide the process. The reason that some of the rootkit detectors relied upon this PSP CID table, however, it was a single point of failure for them. Once Fu2 came along and just obliterated its entry in that table as well, then the detection no longer worked. So what's the structure of a handle table? Every single handle that you get back is basically an index into your process handle table, or it could be an index into the kernel handle table. At the offset within that table that corresponds to the index is the actual pointer to the object itself. So file objects have a certain structure in memory when they're open, and they keep state information. Process objects are the same. Thread objects are the same. These are all pointed to by the handle table. So once you find the handle table of a process or of the system that you're interested in, here's what it looks like. The very top member of that is a pointer to these arrays of objects. So that's what we were interested in with the FU2. Now this is an example of test.exe. Its process ID is 152. And it's a userland process that's trying to open an existing process by ID and then to terminate that process. So it makes a call to open process, and the ID it's looking for is 132. It gets back a handle in H process. Then it makes a call to terminate process with the handle of 3. 3 would be the handle to process 132. Terminate process actually does a call to ntdll.dll with a ZW terminate process. That transitions us into kernel mode. We now go through the system call table, and we're into nt terminate process. This is an abstraction of how it works. It isn't the exact assembly. It isn't assembly level accurate, but it's an abstraction of how it would work conceptually. So we have to translate the handle into an object to begin with, because everything in the kernel operates upon the objects, not upon the handles. The handles are only used in order for userland processing, other threads and so forth, not to have access to the raw data. So it's an abstraction where you can implement your security reference monitor at one place, because since the other processes don't know the address of the object, they can't manipulate it themselves. So here, NT terminate process is going to look up a handle to the object for 03. What its goal is to get back the eProcess structure, and then it's going to make some calls on that. So translate handle to object will look up the current process by ID, which in this case we want 152. So we're going to go to process 152's handle table eventually. So you see there the first blue array that showed up, that is the handle tables, or that's all the processes. Here we're going to go to 152, and then we're going to go to its individual handle table, which is pointed to by the eProcess block of process 152. Within that, it's just a big array. We're going to go to offset 3, because that's the handle we're interested in. At offset 3 will be two things. One will be a pointer to the object, and the other will be the access mask. That's used by the security reference model. However, if you're a driver and you're just doing these decom tricks, you don't have to worry about the access mask. If you can parse these handle tables yourselves, which obviously Foo2 can do, then you can just wipe it out. That's what this slide shows. We just nulled out that entry. So in this case, we would go to the PSP CID table and just null out that object pointer. Therefore, next slide, people who brute force across PIDs or PROS-TIDs would not see us. This was the algorithm used by F-Secure's BlackHat. Anybody from F-Secure here? Don't throw anything at me, please. Last conference, they said they didn't know whether they wanted to shake my hand or hit me in the face. Luckily, they shook my hand because we were at dinner. So what they did was they brute forced over all the PIDs available. There's a limited range of process IDs that the system can use. So they just said open process, open process, open process, several thousand times over all the PID indexes. They would then get back a handle, and now they would have a handle to all the processes that were there. Then they would call another API like ZW Query System Information to get back a listing from the kernel of all the processes. They could compare the two lists, and if there was any discrepancies, then they know they have a hidden process. This is very effective. However, FU2 showed that this could be defeated as well. So now Peter's going to take over and explain how RAID goes about detecting all these different things.
All right. So this is the portion of the talk where we introduce the new ideas, design thoughts, implementations, and then do the demo. So bear with us, and we'll hopefully the payoff will be the demo, and you guys will like it or not. So RAID had, when we were thinking about designing this, RAID had a couple design thoughts. The first was we wanted it to be essentially a complete toolkit. We didn't want to force people to go to other tools because currently you got to take rootkit revealer, you might want a BlackHat, you might want an SVV, and you just combine them and you run them and you see what happens, and you might get varying results. So the idea behind RAID was it's the one-stop shop. Another thing was we wanted to thwart application-specific attacks, and we came up with our own acronym that I'm not even going to bother to pronounce because it's really long. But we use our own secure communication channel. We do not use octals. We use a different method that's randomized, so no octal attacks will work. And you'd have to figure out how we're creating the shared memory segments before you could even think of messing with our communication. Another thought was RAID is not developed with a GUI, doesn't require the .NET framework. If you think of Box's own, you drop the driver, you drop the console, and you go. The idea that you need to install the framework, reboot 3 times, download 200 megabytes on a machine you're trying to do forensic analysis is probably a poor idea. So RAID is, drop and go, which was one of the ideas. And finally, a unique idea we came up with is we wanted RAID to be for both Joe Schmo and the researcher. We want to offer features for the researcher to be able to do research and say this driver is this virus family or this rootkit. But we also want your mom to be able to say clean my system, and won't get a phone call saying I just did something and I don't know what I did. Come home. So those are the two areas we were trying to go with RAID, and we tried to combine it into one tool. Real quick, RAID can run on Windows XP and XP Service Pack 2. Doesn't run on Vista. I didn't put that in the slide, but I don't even have Vista, so I can't even test it. Runs on Service Pack 4. It will give you a nice warning saying it hasn't been fully tested on Service Pack 4. If anyone wants to donate legal license keys to me, I'll develop it out further and put it on different operating systems. It does work on 2000 pre-Service Pack 1. Something changed in the kernel. I didn't have the time before the talk or the weeks before to fully work it out. So support for post-Service Pack 1 is in development and will be soon, out soon. All right, so the communication. Like I said, we came up with a new scheme. We used shared memory segments to thwart crappy and stupid application-specific attacks. These are your hacker, defender, your rootkits that are going to target your printfs and modify what you're printing out to the user, that kind of stuff. It really pains me to acknowledge they exist because it's just, it takes no thought to do that. So we just wanted to make their life a little harder. What we do is we use a shared memory segment that's shared between the user land and kernel. The shared memory segment has a random name, so it changes every time RAID is run, so they can't predict the name. And we use it to pass information back and forth, just like an octal. I can send a command, I can receive a request back, and I have my buffer filled out, just like octals, but without the potential vulnerabilities of octals. We also use, obviously we're also going to use randomly named events to communicate, signal back and forth between user and kernel. And finally, we'll talk about this further in the difference-based or cross-view comparison for process detection. What we're going to do is we're going to spawn a process from userland that our kernel driver initiates. So it's going to look like you double-clicked on it from userland. However, it's actually being spawned from the driver. It goes through explorer.exe. Anyone hooking a specific open or create process call from the driver will not see it. It looks exactly like every executable you ever run. It's a pretty neat way, and it's very unique the way we're doing it. And of course, the process is dumped on disk. It's not something copied. The process name is random. We randomize some things in there to keep them from preventing this process from spawning. So what is RAID not? This is an important slide here. RAID is not a replacement for common sense. If you get an email from your ex-girlfriend and she cheated on you, she probably doesn't want to be with you. And if the email says, I love you, as we saw with the love bug, there are a lot of people who are going to take that chance and download the file. Don't. It's not a replacement for common sense. RAID will not keep you rootkit free. I can't stress that enough. What we're doing with RAID is it's a cat and mouse game with rootkits. You've heard it at every talk almost on this track. We're showing our hand, essentially, detection-wise. We're detecting as much as we can. We're doing the best job we can. It's not foolproof. It won't be foolproof. The malware authors will always have the upper hand because they're going to always be one step ahead because they're going to see what we're doing. So it's important to keep that in mind. And we'll keep updating RAID as more methods come out, and especially with virtualization, we're looking into that and things like that. But this is where we are right now, and the design was for it to be the best at this point in time. And tomorrow or in 4 hours when Joanna presents, it might not be. So it's just important to keep that in mind, that the game, it's always changing, and just, so we have to evolve with it. Things RAID won't do, it won't find hidden processes. It will find hidden processes. It won't find hidden files, registry entries, or directories. This is a feature that's not currently in the works, and there's no plans for it. So that's something that we had to pick and choose what we wanted in the time frame we had, and that was something we left out. RAID does not restore driver, ERP, IDT, and MSR hooks. I am doing some research on the IDT restoring, but the ERPs and MSR stuff is not in the works. It's too dynamic to figure out what the original value was. At the moment, RAID won't identify hidden drivers. That will be added in the next version, for sure. And finally, and this is the difference between a lot of different talks, if the driver is hiding in plain sight, meaning I can run device tree from OSR, or I can run some device tree that dumps the drivers, RAID won't pick it up because it's not hiding. And it's important to keep that in mind. If your rootkit is hiding in plain sight, and by that you mean it's not hiding at all, then you can just look at a device tree and see, hey, that device doesn't look familiar, and look at it from there. So that's something RAID just to keep in mind. All right, so originally I had this really cool thing where RAID is an acronym, so the A was highlighted and the A was highlighted and everything else was gray, but you won't be able to see that, so just pretend like it's there because I worked hard on that. It took me a good 5 minutes. So RAID's analyzing mode, it will analyze the user mode for user hooks. So if it will scan the process for, it will find the executable in the process, It'll check the import address table. If the import address table points to important modules, and these are going to be your kernel 32, NTDLL, WinSock, IP help API. If it points to those modules, it's then going to make sure the pointers are valid, so it doesn't point to the relocation section. It points within where it's supposed to. And it does the same for the export address table. It'll check the, and again, we have a list of important modules, and we verify that the export address table is pointing in the code section, and it's not pointing in the relocation section. Some people try to do that. And it's not pointing outside the module. So those are things we try to do with the export address table. Kernel hooks. This is much more important, and it's something that is an everyday problem, especially seeing it in spyware now. First, we verify the KE system service descriptor table, which we'll refer to as the SSDT, or the KI service table. It verifies the function pointers, making sure all the function pointers point within the module it's supposed to. We know all the function pointers for no reason whatsoever. They have to point within NTOS kernel. Once we verify they're all pointing within NTOS kernel, we take it a step further, and we load NTOS kernel off of disk. We calculate where the KI service table is in the file locally using a 90210's method, which is pretty good because Kaspersky actually randomizes where it is. And then we just do instruction comparison to make sure the first 12 to 30 bytes, it depends on what we're doing, are the same. So after you get deep enough in a function, you're not going to be able to change the instructions because you're going to throw off the program enough where it won't know what's going on. So you're going to see inline hooks within the first 20 instructions or so. We also check the IDT. We make sure that all the IDT handlers, like your page fault handler, things like that, all point within NTOS kernel. We also then check the actual function handler itself, and we make sure that the function handler doesn't have a known inline hook. This is a Band-Aid. I'm going to actually look into verifying it byte by byte or instruction by instruction, but right now we just do a check, and we do a signature check, essentially, on the preamble. And we also check the system enter MSR to make sure it points to the NTOS kernel. It's a pretty easy check. And finally, we have a list of important drivers so we don't waste our time looking for hooks, and you'll see how fast we actually are able to scan the system. We'll make sure all the ERPs are legitimate. So that's the kernel analysis mode. All right, so those of you who have seen Joanna's talk about Deep Door, which was, like I said, everything's evolving, so she's got a new thing that hides TCP connections, and we're just picking up the Deep Door detection. So we are able to analyze and find Deep Door and UAY like hooks. And essentially, this is low-level NDIS hooks, which allow the complete stealth command of control channels. So you can essentially hide, with it, you have your own TCP IP stack, and you can bypass the Windows existing one, and you can hide your own ports. You can attach to ports that are owned by other processes. You can do a lot of different things with this. And we know Alexander, I can't pronounce his last name, I do apologize, but the talk after Greg's, before Joanna's, that one is going to cover a lot of this, so that one should be interesting, and he's talking about how to bypass firewalls and stuff. All right, so process detection. We're pretty good at process hiding, so can we be that good at detection? Well, we sat down and we thought about what do we want to do with process detection, and what are the problems with the current process detection mechanisms. The major one is they're relying on structures that can be modified quite easily. So what's the common thing that all processes have to have? A process has to have a thread, and it has to have an eProcess structure and an eThread structure. With that, we came up with the idea of creating a signature for those structures. And this signature had to be so that it couldn't be zeroed out. Essentially, if you find our signature, which we're actually going to tell you, so it's not that hard to know what our signature is, you can't null it out so that we won't pick it up. The signature has to be unique. It can't be all over memory, and that also pertains to the signature. It can't have too many false positives, if any. So the signature we came up with, which is pretty good, I say pretty, it's decent. The service table pointer. Every thread has to have a pointer to the service table. If you zeroed it out, you will crash the thread and the process. The service table can either point, depending on the thread, if it's GUI or not, will either point to the KE service descriptor table shadow or the KE service descriptor table. We locate pointers to either one, and then we know that that's a thread, and we look back, find its process, and we keep what we call a master list in the kernel of all the processes we can see in memory. And then what we do is we spawn a process, as we said earlier, with a random name. It looks exactly like you double-clicked on it. It generates a process list that's visible to the user. It's essentially a snapshot if you picture Task Manager being sent to the kernel. So if the process is visible, then we just diff the two lists. Anything that's not in one that's in the other is considered hidden and is reported to the user. And we'll talk about the actual identification of the method they're using and stuff. All right, now this is a really unique feature, and virus analysts and stuff are going to like this a lot. we have the ability to dump processes. This will allow security analysts to take a hidden process or a hooking module, dump it to disk. Even if the file is hidden on disk, we dump it, rename it, and we put it in a different directory. So those are the ways we do it. It's also important to note, and Metasploit has done this, is that you don't need to touch the hard drive to load a hooking module. You can just load it right up into memory and execute it. So keep that in mind when you're dealing with those kinds of things. So as I said, we allow the forensic analysis of hooking modules. You can, if the hook is found in kernel and the hooking module is identified, we give you the option of dumping it. However, as you can see at the bottom, this feature is in beta, and you'll see during the demo, it doesn't work to its correct potential. It always finds the executable module, but we want to be able to dump the actual DLLs in the address space as well. So we're still working that out. It will not be included in the public release this week, but it will be included later. We're not holding it because we want to sell it. We're holding it because it doesn't work correctly right now, or fully. All right, so identification. Once you've analyzed the system and you found all these different types of hooks, you have to identify what kind of hook it is. RAID identifies a ton of hooks. You've got your SSDT overwrite inline hooks, IAT overwrite inline hooks, your EAT overwrite inline and forward hooks, your ERP hooks, your IDT hooks, your MSR hooks, and then open block and characteristic protocol hooks, which are going to be your deep door-like zone alarm hooks. And we also offer the user the ability to identify the type of hidden process. So if we recognize the method being used to hide the process, we'll report to the user, and based on that event, we can then decide, we can give the user a selection of what they want to do with that hidden process. So the two types we recognize are DCOM and PSP-CID table modification, and we'll talk about that in a second. So we had to come up with the list of what methods we want to identify. The two major ones are obviously FU and FU2. They're most prolific. FU is the most widespread rootkit. FU2 is not stable enough with some of the more advanced features to be bundled in spyware, which is an achievement in itself. So if the process is visible by walking the active process links, or is not visible by walking the active process links, it's therefore hidden with DCOM. Automatically we know that. However, we then check the PSP-CID table. If the process is not in the PSP-CID table, it's hidden with FU2, since FU2 combines FU and the PSP-CID table. If it is in the PSP-CID table, we know it's using FU method, and we can then mark it and report to the user what type of method it's using, and you'll see that in the demo, hopefully. All right, so I don't know how many of you were here earlier this morning when they talked about, I don't remember the term they used, but it was, firewalls now act exactly like rootkits. They're going to hook low level, they're going to do deep door hooks. So how do we know what is good and what is bad? And the behavioral analysis was one of the first ideas that came up, and it's been in academia all over the place. And the problem with it, and I've seen rootkit detection tools based on it, is a rootkit will just mimic the behavior of a firewall and bypass it completely. And so it's really, I felt it was a moot point to try behavioral analysis. So what I did was, and this, the problem with this is that every time a driver gets updated, you have to come up with a new signature. But the signature is based on 4 values. You have to have a matching point on all 4. It's almost like a fingerprint. You got to have 5 or 6 point match. Same thing with the driver. We have to be able to match each point. Once it's a match, we know that this driver is installed by this product. We report to the user, and this is good for everyone's mom. It'll say, this hook is installed by this product. Do you have this product installed on your system? If you do, you just type ignore. They will ignore the hooks, and you won't have the option to damage your system by restoring the hooks that were installed there by a product you legitimately installed. So currently, we support the following firewalls. As you can see, it's a list of them. Quick note, Outpost, I don't know if any of you use it. They are using userland hooks. I was a little shocked. So if anyone from Outpost here, come and talk to me. I'll give you code. But yeah, so that was a surprise. But it identifies about 253 hooks installed by all these products, and I'll keep adding as I have time. I've toyed with the idea of putting in a feature into RAID, which will actually dump the signature, and then you can send me the text file and I'll add it in. I'm afraid someone's going to get creative and convince me that this is a firewall and really it's the rootkit, and then I whitelist the rootkit. So I'm a little apprehensive, and it won't be in the public version for sure until I decide. All right, rootkit elimination. We've analyzed the system. We've identified you've got some firewalls, you've got some rootkits. Things are going whack for you. What can we do for you? Well, we offer a couple elimination options. You can restore the original values of the inline hook. So if there's a jump written in memory, we'll overwrite the jump with the actual bytes that are supposed to be there. I think this was called, what was it called? Semantic, the byte-by-byte comparison? In the earlier talk, they had their own term. I can't keep track. Everyone makes up their own terms. So semantic verification, we do it as well. woohoo. So we're able to restore it using the same method. We also restore the function pointers in the SSDT. And finally, we restore the EAT. So if a driver had its export address table modified, which you see in a lot of, which you're seeing more now, and you also see in a lot of firewalls, we can restore that as well. We also offer some unique restore options for processes. The funniest one is actually decom in reverse. The idea that you unlinked it, but what's stopping me from relinking it back up? So we'll probably show you that as well. It just puts it back in Task Manager. It appears right back after it disappeared. It's nice. You can also close the process if you don't even want to bother to relink it. Doesn't matter either way. With FU2, the process, the operating system is so unaware of the process on the system that doing anything to it is not good, and we don't offer anything just for everyone else's own benefit. So that sort of wraps up the talking portion. And we're now going to, this is a demo. There's at least 6 rootkits, but there's more than 6 hooks. I think there's about 15 hooks, not including the deep door hooks. And the song says it's 10% luck. For those of you who develop on VMware, you'll know that VMware and rootkits and things like that, it's a crapshoot. It's been good all week. I make no promises. I've got a backup, so we're just going to do this. As you can see, there are also going to be 2 hidden processes, WinDBG, RAID, all on VMware, and I'm going to break in WinDBG to show you the hooks, so there's no black magic, nothing up my sleeves. So let's do this. Can you guys, what's the? All right, so we're going to spawn. We got to go full screen. I'm going to enter full screen. Is that better? Yes? All right, because I got to be able to see what I'm doing too. So, all right, so we're going to hide calc, the first calc, using just regular old FU from 2000, whenever, 2. FU's hidden, and that's the calculator on my left, your right, just so we can keep stuff straight when I try to close things. We're going to put this one on my right, your left. We're going to use FU2. Now, I mentioned that there's a -PHNG option, which stands for process hide no GUI. We're not using that. It's hard enough to do this demo. PHNG bypasses everything except dark spy, as far as I know, still. But it's pretty iffy on us sometimes with locking and things like that because we really hose the system. So we're just going to go with PH and hope things work out. Oh, okay, VMware. All right, so both processes are hidden, and you can see they're running, and I'll just click on stuff so you know that they're both legitimately responding, and I haven't frozen them. All right, and just real quick so we can go over it. Every one of these drivers is loaded on the system already. I'll show you that they are, just so you believe me. Real quick, basic MDL flags is your SSDT index hook. MIGBot is your inline hook. ERP hook is what it is the file name. It is an ERP hook. It's 3 ERP hook, actually. Byte hook is a 1-byte hook in 4 NTOS kernel functions, or 3. System enter is a system enter hook, and then NDIS hook is deep door and some export address table functions. The other 2 drivers are not actually loaded. So, so as I promised, it's just 2 files. Give me a second here, just so we can. Now I'm going to break in WinDBG. This is always the interesting part. All right. There's your 1 inline hook. Another inline hook. Another inline hook. Another inline hook. You see where I'm going with this. And those are the ones I can show you. I'll also show you the service descriptor table just so you know that that's legitimately hooked. So there's the index hook. We're going to start WinDBG back up. That's where we hold our breath here. We good? Everyone can see? All right, so what I'm going to ask you to do is direct your attention to the folder above, because I'll scroll back up. You're going to see a file dropped there and deleted. Watch the task manager as well. You'll see something spawned. It won't be in any language you recognize, nor I recognize, actually. So real quick, your scan options. One of the components of RAID is why waste time scanning everything when you know what you're looking for? Default is scan. Obviously, that's what I'm going to run. I offer scan processes, which just scans processes. Scan kernel just scans the kernel. Scan hooks just scans for hooks, but that includes userland and kernel mode. Scan all scans everything. It's pretty basic. And then you have the log option, which will log to a file, randomly create random file name in the current directory. This is just because the console output is a little heavy to read sometimes, and if you're on a pretty bad system, you're going to be hurting reading it. So it's just another option, and you can send it to someone to look at if you don't know what you're doing. Don't send it to me, please. So let's do this. All right, this is for my own protection. If there's something wrong and you don't agree to it, don't run it. So I agree to it, of course, my own system. 8 products, 253 hooks, 24 hooks found. Here's we go. Watch the there's the file. It's in the task manager. It's running.
We just spawned a process from the driver. RAID runs completely as a driver.
So you just saw it work successfully, and that happens every time. All right. So yes. So what we're going to show you now is the dumping process functionality. And we might take a question because it does take its time doing this. Keep your eye on the folder. If we can get one question. Anyone have one question? Or no questions, that's fine too. OK, we'll just wait then.
So with the dumping, what that allows you to do is take it back for forensic analysis. You can slap it into IDA Pro and other reverse engineering tools and determine, you may know that it was there and it was hidden, but now what in the world was this thing doing? And you're really going to need a human engineer to probably try to figure out what its intent was.
So as you can see, it's only dumped 2 of the DLLs from the address space. Like I said, this isn't going out in the public version because of reasons like that. The file size is also a little off. The page rounds up, so the file might not be aligned at the end of a page, and we might dump extra bytes that the executable won't recognize. And Windows has this little thing where if the file size is bigger than the size of the image value in the PE header, it's considered not a valid Windows process. So that's just something. And this is FU2. We are not going to do anything. FU2 nukes the process ID just for the fun of it. It is annoying. I don't know why I did that. That was pretty stupid of me. But so you can see it does nuke the process ID. So that one was, we're going to do nothing with that. Now you have your hook menu. You can restore just this hook and continue on. You can restore all the hooks. Saves a lot of time. You can ignore this hook, just continue on. You can ignore this type of hook. And this is a feature that you should use if you have a firewall we don't support and you're getting hit with like 56 hook functions. They're going to all be of the same type. You just ignore them all and continue on. You can only display, or you can dump the file containing the hook, which we're not going to do. But we will restore all the hooks. Now notice the file was deleted. It's off the system. And now we'll scroll up and we'll just go through some of the outputs so you can see what's up. And I am going to put in new line characters. I'm not allergic to them. I just didn't put them in earlier. So as you can see, the inline hooks are all there. They've been detected and restored. The ERP hooks, which is what Jamie was talking about, for hiding ports, are all there. They haven't been restored. The EAT hooks have been restored. And this is the deep door, the NDIS protocol characteristics. It tells you that it's been modified, like the send complete handler has been modified, and it's pointing to the NDIS hook. So it's picking up deep door and things like that, and I'm not sure how it will fare against the talk coming up, but we'll find out, and we can make modifications if we need to. So that's pretty much it. We can do another run if you want to see how much time do we have left. Yeah, we can do another one real quick and show you the relinking. I've had that thought. That's as far as it's gone. Do apologize.
Y'all realize it's supposed to last until 12:30, right? Yeah. Okay. You ran it from a folder, and that folder didn't reside.
Yeah. So now we have the processes, and what I'm going to show you is watch Task Manager. It is now appeared back in Task Manager.
Calc just got relinked.
So it's decom in reverse, FU essentially, in reverse, which is a neat little trick we use. And then now it's offering us the, well, no, we're not going to dump the file. And that was the scan process only option. So, and then real quick, just for everyone's own benefit, you notice the jumps are now gone. All of them. And you'll also notice that the query system information has been restored. Yeah, it's been restored. So essentially everything I said it did, and it always happens like that. Do we have any questions?
What user level do you have to be to run the program? You run as an average user, or do you have to?
You have to be able to install a driver. Yeah.
When you're taking the jumps back out, right, or doing the relinking so everything's running smoothly, how are you doing that? On a signature-based approach, or
You're asking how are we doing the relinking?
yeah, because I would think you have to know every process.
No, it's actually one line of code. The question was how are we doing the relinking, and the answer is quite simple. Active process linked is a list entry structure, and so essentially we're just removing ourselves. There's a function or macro in the DDK that's called insert list at tail, and all we need is the eProcess and the system eProcess, which we can obtain by 2 API calls, and we just add it back in. So it just gets added to the end of the list and reappears. It was sort of shockingly simple. And then the well, I start at the beginning of the function and I go down however many bytes I've decided. Essentially, because I'm able to find the KI service to table from disk using, as I said, 90210's method, I know where the function is locally, and I just start there, and I start in memory, and I just back and forth, and it's, it's pretty easy, and it's a legitimate way to do it. And, it just depends how deep you want to go, and you just make sure you line up on how deep. Well, I mean, one could make the, well, this doesn't run on Mac, but one can make the assumption that Joanna's about to hose us. It depends, and like I said, it's a cat and mouse game. I'm looking forward to Joanna's talk. It's the last one, but I encourage you all to stay and see it. As far as I know, everything I ran it against, it worked fine. Shadow Walker, you can get past it. I know, I mean, we know how to with Shadow Walker. But it still picks up the IDT hooks, so you'll know something's up. UAY, it picks up because of the NDIS hook detection. So I mean, right now it's pretty good, but as we get into the more virtualized technology, we're going to see greater problems and things like that. Oh, sorry. Well, the problem with restoring ERP hooks is we have to know what the original address value was, and we don't right now. No, and it's not in the works either. That's not, I'm sorry, yeah. I'm sorry? No, I said it doesn't recognize rootkits that aren't hiding themselves, but nothing will. Essentially, if a rootkit's not hiding itself, it's in plain sight, and all you need is, I recommend, OSR has a program called Device Tree, and it'll list all the drivers that are installed in your system. You'll see it. Yeah, when I said that, I was saying that there's some people have taken the stance that if I don't hide my driver, there's nothing to find, and that's true, but it's also easy. If the administrator knows what they're doing, they can go through with Device Tree and say, that device doesn't look familiar. Any other questions? Or,
do you have a problem with other protection software? Whether you had a problem with other protection software, some of
Well, we don't have any hooks, so no one thought we were rootkits. Kaspersky messes with the Windows like I've never seen before, so that was quite an experience getting RAID to work with it. But RAID does work happily along with Kaspersky now, along with all the other firewalls you saw. It runs fine. So yeah, I mean, we don't do any hooking, so we've not had that problem. I don't know if the antivirus will take the stance that this tool will be a problem, and they'll say, I don't know, they're weird like that. So.
And a lot of the protection software tries to block certain API calls. RAID is bleeding edge, which means we're using pretty much all the rootkit technology that's in the 2nd generation advanced digital weaponry class that taught on Monday and Tuesday. We use that for good purposes. So it's very bleeding edge.
Yeah, if you dump this in IDA and look at what we're calling, you're not going to see too many API calls. We try to avoid them like the plague, just because I don't trust API calls. And like Bill said, we're on a system that's potentially owned, so anything we get back could be tainted. So we take the stance that the less we get back is better. So we try to avoid relying on any information. We make very few API calls. Interesting question. I don't have internet in my room, and I don't plan to pay for it, and I don't plan to use BlackHat's internet. So
somebody give him 12 bucks.
It's 25, but no. I'll probably dump it to disk and give it to Jeff today, and hopefully it'll go on. Along with the slides, I know for those of you who opened your laptop and realized that everything was different, do apologize, that happens. But yeah, it'll be on BlackHat, it'll be on rootkit.com, and it'll be on OpenRCE within the week. And just use it as your own risk is all, for my own protection. Any other questions? All right, well, thank you very much. Oh, so, yeah.